All right, let's start. It's been a while since I lastly record. I'm very dark here. Um, well, I can't help it because there's no additional lighting other than that. So it's been quite a while since I have last recorded. Um, there are a lot of things happened. I switched my companies, and it's been kind of busy. I couldn't do anything on YouTube. So, yeah. Anything else? I'm just happy and healthy. No problem. No personal problems. Anything. I was just simply busy. So I'm going to resume um, what I was doing before I got busy. Right. Well, I am busy right now, but I just somehow managed to find some time to do it. Right. So today, what I'm thinking about doing is to read read an article, tech blog. Where is it? From Netflix. Let me check if this is public. Uh, this public article. How can I verify that? Let me sign out from my account. It's a paid account, so if I open up this article again without an account and I can open it, that means it's for free. Okay, great. So today I'm going to read this article from Netflix, Scaling Muse, about apparently scaling up a service hosted on Netflix. I have a bunch of tech blogs from Netflix that I've bookmarked and I haven't read any. So this is one of it. Scaling Muse, how Netflix powers data-driven creative insights at trillion row scale. Okay, let me make it bigger for you because I'm suspecting you have a hard time reading it. Alright, I think it's good. Yeah. At Netflix, we prioritize getting timely data and insights into the hands of the people who can act on them. One of our key internal applications for this purpose is Muse. So Muse is apparently how do you call what's the opposite for online transaction on ONTP, online transaction process, or process. On top is online on lap and on tap, right? OLTP, online transaction protocol, and on lap, online analytics. Nope. On tap, IT. Well, usually we call it on TP, online. OLTP application. Here we go. On tap and on lap. OLAP. So OLAP is online analytical process or something like that. It's in Japanese. Let me translate it. Can I translate it to English? Not from here. Okay, here. Here. Online analytical processing and online transaction processing. So online transaction processing is usually what we call web applications, where you could interact with the web dashboard or something like that. So you could do your tax, so you could do purchasing, your cab, your groceries and stuff. Whereas online analytical processing, which I pronounce it usually OLAP, is an analytical service that basically does analytic analysis on the business operations and transactions that's been made, mainly on OLTP. Well, usually OLTP. So the business owner of the company, of the owner of the product, can enhance their features and stuff. So that's what I understand. So Muse is OLAP applications, to my, well, in my understanding, if that's correct. Because it says timely data and insights, getting timely data and insights into the hands of the people who can act on them, right? So Muse ultimate goal is to help Netflix members discover content they'll love by ensuring content they will love by ensuring our promotional media media is as effective and authentic as possible. It achieves this by equipping creative strategies and launch managers with data-driven with the data-driven insights showing which artwork or video clips resonate best with global or regional audiences and flagging outliers such as potentially misleading clickbaity assets. Flagging outliers. I don't know what this means. Outliers. Alright. I need to put it in my vocabulary list. Let me just do it real quick. That's how you call outliers. It's interesting. No, I didn't actually copy it. Well, my new company gave me Windows machine, so keyboards work kind of differently when you copy and paste, right? So you use Control plus C to copy on Windows, whereas you type Command and C to copy, which kind of sucks. It's such a simple operations, but there are two different key combinations on different platforms. Well, enough of digression. Let's resume. These kinds of applications fall under our online analytical process. Okay, yeah, sure. That's what I was talking about, right? A category of systems designed for complex querying and data exploration. However, enabling Muse to support new, more advanced filtering and grouping capabilities while maintaining high performance and data accuracy has been a challenge. Previous posts have touched on artwork personalization and our impressions architecture. In this post, we will discuss some steps we've taken to evolve the Muse data serving layer to enable new capabilities while maintaining high performance and data accuracy. Oh, this is how it looks like, the Muse. Performance summary results during explore. What can you get in this control panel? Impression distribution. Oh. So I'm not sure if, like, you see a lot, like dozens of how do you call it, thumbnails. Yeah, dozens of thumbnails, and I'm not sure if this is like clips from one episode or they're just thumbnails for each episode. Not sure. But as far as I can see, it apparently collecting data from end users and show what kind of how each of the clips performed based on average, right? An evolving architecture. Like many early analytics applications, Muse began as a simple dashboard powered by batch data pipelines. Spark. I heard of it. It's Apache Spark, right? Equivalent to AWS what? Glue, is it? Equivalent. Apache Spark on EMR doesn't have single equal. Oh, really? Or is it Airflow or what was the other? Apache. It's like Q. Apache Q. Kafka, yeah, Kafka. That's what I was talking about. It's Apache Kafka equivalent in AWS is Kinesis. There's also Amazon managed service for Apache Kafka, but also which is MSK, and also there is a service on AWS that does a similar thing as Kafka. Okay, Kinesis. Anyways, let's resume. And a modest druid. Oh, I have no idea what this is. Let me go to it. Apache Druid is a high-performance real-time analytics database designed for quickly querying large volumes of data. Okay, got it. Apache Spark is an open-source analytics engine for processing large-scale data, enabling tasks like batch processing, machine learning, and stream processing. That's cool. Open-source analytics engine. That's cool. Well, there are a lot of things. Holo, Java library for efficient in-memory storage. So it's like Redis. Depends on if it's Q, a key to value, or access to moderately sized read-only datasets, making it ideal for high-performance data retrieval. Apache Iceberg is an open-source table format designed for large-scale analytical datasets stored in data lakes. It provides a robust and reliable way to manage data in formats like Parquet or ORC within cloud object storage or distributed file system. Okay, let's just skip. So what was Druid? Druid, I completely forgot. In a minute. High performance real time analytic database. Okay, database. It's a database for quickly. Okay, good. Yeah, because it says cluster. Yeah, it's a database. As the application evolved, so did the user demands. Users wanted new features like outlier detection and notification delivery, media comparison, and playback, and advanced filtering, all while requiring lower latency and supporting ever-growing datasets in the order of trillions of rows a year. One of the most challenging requirements was enabling dynamic analysis of promotional media performance by audience affinities. Affinities meaning crowd or something. Okay, it's not crowd. Shinwasen. Let me put that to my vocabulary list. Okay, here. Internally defined algorithmically inferred labels representing collections of viewers with similar tastes. So similar to Kyocho filter. I don't know how to say it in English. Collaborative filter. I'm not sure if this is a thing or just direct translation. Collaborative filtering. Okay. So collaborate. So it kind of, yeah, it's kind of coming off as collaborative filtering here to me. Where was I? performance by audience affinities. Internally defined, algorithmically inferred labels representing collections of viewers with similar tastes. Answering questions like, does this specific promotional media resonate more with character drama fans or pop culture enthusiasts? Require augmenting, required augmenting already voluminous impression and playback data. I'm lost. Hold on. Answering question. Okay. Require. Okay. Because this was so long, I was just lost the grammar. Supporting filtering and grouping by these many-to-many audience relationship led to a combinational explosion in data volume, pushing the limits of our original architecture. To address these complexities and support the evolving needs for our users, we undertook significant evolutions of Muse's architecture. Today, Muse is a React app that requires GraphQL layers served with a set of Spring Boot gRPC microservices. In the remainder of this post, we will focus on steps we took to scale the data microservice, its backing ETL, extract, transform, load. And our Druid cluster. Specifically, we've changed the data model to rely on hyperlog HLL. I don't know what that is. I just don't know. Hyperlog sketches use Holo for access. Well, specifically, we changed the data model to rely on hyperlog sketches. Use Holo. Oh, I mistakenly opened it. For access to in-memory pre-computed aggregates and taking a series of steps to tune Druid. To ensure the accuracy of these changes, we rely heavily on internal debugging tools to validate pre and post changes. What was Holo? Holo, is it Netflix OSS? Wow, that's cool. Netflix does everything. Holo is a Java library for efficient e-memory. E-memory, so it's like Redis. Where was I? No. Holo. Here. And taking series of steps. Okay. I have read it. Split view. Okay. I'm not interested in that. Creative strategist. Muse front end React app, and behind that is Studio Edge federated GraphQL layer. Muse primary backend domain graph service. Augments raw metric data with relevant metadata, calculates derived metrics, warnings, etc. So it's like how do you say network database? How's that called? Graph database. Yeah, that's what I wanted to say. Probably it's that. Primary backend domain graph service. Yeah, so it sounds like that. Right. Muse data microservice, Spring Boot gRPC service. So memcached is also in-memory database, if I'm not mistaken. Holo feeds, Holo. As I mentioned earlier, it's also memory database. Druid is I have such a low memory. Druid. Okay, it's a database. Yes, it's a database. Sorry for returning so many times. Returns fact-based data like number of impressions plays, abandoned plays, etc. Metadata services are okay. Good. Offline Spark, daily pipelines load, Druid and Holo V. So this is Spark was it Q? I forgot. open source analytics engine. All right. Okay, analytics engine will load Druid and Hollow feeds. That's what it does, apparently. Moving to hyperlog sketches for distinct counts. Some of the most important metrics we track are impressions, the number of times in a set is shown to the user within a time window, and qualified plays, which links a playback event with a minimum duration back to a specific impression. I didn't catch that. Number of times, this is okay, this understandable. Qualified plays, what is qualified plays? Is there any unqualified plays? Regged users and something like that? Sure. Which links playback, which was playback event with a minimum duration back to a specific impression. Which links a playback event? Okay. Which links with a minimum duration? Back to a specific okay. Yeah. Because I was confused because links with this was. I was thinking this will link a playback event to a minimum duration, but then it said back to blah blah blah. So I was confused, but it's a playback event which whose duration is a minimum, and links that to a specific impression. Okay, understandable, understood right now. Understand right now. Calculating these metrics requires counting distinct users. However, performing distinct counts in distributed system is resource intensive and challenging. For instance, to determine how many unique profiles have ever seen a particular asset, we need to compare each new set of profile IDs with those from all days before it, potentially spanning months or even years. Yeah, that's going to be a lot. For performance, we can trade accuracy. The Apache data sketches library allows us to get distinct count estimates that are within a 1 to 2% error. This is tunnable. I heard of that. Ooh, that's cool vocabulary. Let me put that. Tunable? Okay, tunable. Okay. It's tunable with a precision parameter called log k, 0.8% in our case with log k of 17. We built sketches in two places. I don't know these maths going on in here, but all I understand is that there's no problem with the 1 to 2% error when we try to get distinct counts estimates. During Druid, am I pronouncing it right? Even Druid or Druid?
Druid.
During Druid ingest, we use HLL sketch build aggregator with Druid rollup set to true to reduce our data in preparation for a fast distinct counting. Rollup. During our Spark ETL, we processed pre-computed aggregates like all-time impressions per asset in the form of HLL sketches. Each day we merge a new HLL sketch into existing one using a combination of LL union and HL union aggregation functions added by our very own Ryan Berry. Okay. Merge new HL sketches with existing ones in iceberg tables. And then this table will be licensed to Hollow. Get HL dismissed from sketches and write those into Hollow feeds. Build and store HL sketches in Druid data sources during ingest using a Hadoop job. HL has been a huge performance boost for us, both within the serving and ETL layer. Across our most common OLAP query patterns, we've seen latencies reduced by approximately 50%. Nevertheless, running approx count distinct over large date ranges on the Druid cluster for very large titles exhausts limited threads, especially in high concurrency situations. To further offload Druid query volume and preserve cluster threads, we also relied extensively on the Hollow library. Hollow as a read-only key value. Okay, so Hollow is a, like I said, it's Redis, like key value store. So I don't know why they're using Hollow. Well, but probably they wanted to use Hollow library to. The problem is software engineer often. I'm just curious about why Hollow, not Redis. But let's just leave that for later and just keep going on. Our in-house Hollow infrastructure allows us to easily create Hollow feeds, essentially highly compressed and performant in-memory key value stores from iceberg tables. Okay, because they wanted to use iceberg. Which was stated here. Well, still I don't get why this is offline and why this is online. Not really sure what this means. Well, it means it's offline and it means it's online, but aren't they both online? I'm not sure because they have to be, well, I don't know. I'll figure it out later. Stores from iceberg tape. In this setup, dedicated producer servers listen for changes to iceberg tables, and when updates occur, they push the latest data downstream consumers. On the consumer side, our Spring Boot application listens to announcements from these producers and automatically refresh in-memory caches with the latest dataset. This architecture has enabled us to migrate several data access patterns from Druid to Hollow, specifically ones with a limited number of parameter combinations per title. Hold on. This architecture has enabled us to migrate several data access patterns from Druid to Hollow, specifically ones with a limited number of parameter combinations per title. I don't know what that means. Access data patterns with a limited number of parameter combinations per title. Well, basically, there are few variables to narrow down searches, right? So it's because it's limited combinations per title. Okay. One of these was fetching distinct filter dimensions. For example, while most Netflix branded titles are released globally, licensed titles often have rights restrictions that limit their availability to specific countries and time windows. As a result, a particular licensed title might only be available to members in Germany and Luxembourg. In the past, okay, that's what they mean by title, like per title. Okay. In the past, retrieving these distinct country values per asset require issuing select distinct query to our Druid cluster. With Hollow, we maintain a feed of distinct dimension values, allowing us to perform stream operators like the one below directly on a cache dataset. Returns possible filter returns possible filter values for dimensions, just countries. Okay, list, get dimensions, map. It's a map. Hollow consumer lookup, movie ID, return dimensions, get or default. Dimension ID list of string. Store comparators, dimension get name to list. Dimension ID, what's that? Okay, dimension ID here. Although it adds complexity to our service by requiring more intricate requests rather than a higher memory footprint, pre-computed aggregates have given us greater stability and performance. Accessing memory hollow feed with near instant query time. Severe performance in case fetching distinct dimensions, we observe query time drop from hundreds of milliseconds to just tens of milliseconds. More importantly, this shift has floated high concurrency demands from our Druid cluster, resulting in more consistent query performance. In addition to this use case, cache pre-computed aggregates also power features such as retrieving recently launched titles, accessing all-time asset metrics, and serving various pieces of title metadata. Let me mute my microphone for. Excuse me. Tuning Druid, even with the efficiencies gained from HL sketches and hollow feeds, ensuring that our Druid cluster operates performantly has been an ongoing challenge. Fortunately, at Netflix, we are in the company of multiple Apache Druid PMC members like Maitas and Jesse, who have helped us writing out every ounce of performance. Some of the key optimizations we implemented include increasing broker count relative to historical nodes. We aim for broker to historical ratio close to the recommended 1:15, which helps improve query throughput. Tuning segment sites by targeting the 300 to 700 megabyte sweet spot for segment sizes, primarily using the tuning config target parameter during ingestion. We ensure that each segment a single historical thread scans is not overly large. Leveraging Druid lookups for data enrichment. Since joins can be prohibitively expensive in Druid, we use lookups at query time for any key column enrichment. I'm not familiar with Druid, so I don't know what's the difference between joins and lookups. Since there's no lookups in relational database, but apparently, let me see what that is. Lookups are a concept in Apache Druid where dimension values are replaced with new values, allowing join-like functionality. Applying lookups in Druid is similar to joining a dimension table in data warehouse. For the purpose of these documents, a key refers to a dimension value to match, and a value refers to its replacement. So if you is there any motivation of this? It is worth nothing that lookups support not just use cases where keys map one to unique values such as country code and country name, but also support use cases where multiple IDs map to the same value. Multiple app IDs map into a single account manager. When lookups are one to one, Druid is able to apply additional query rewrites. See below for more details. Hmm. Let me read it once again. Uh, I said nothing, but it's noting. Sorry. Okay, lookups do not have history. They always use the current data. This means that if the chief account manager for a particular app ID, oh, this is super. Hold on, this was super small for you guys. Sorry. Particular app changes, and you issue a query with lookup to store app ID account manager relationship. It will return the current account manager for that app ID regardless all the time range over. Lookups are generally preloaded in memory on all servers, but very small lookups, on the order of few dozen to a few hundred entries, can also be passed in line in native queries. Queries time using the map lookup type. Okay. That's why it's faster because it's spread on memories, preloaded. Right, there we go. Where we are. Enrichment, optimizing search predicates. We ensure that all search predicates operate on physical predicates. Search predicates. It's predicate. 述語ね predicate. Operate on physical columns rather than virtual ones, creating necessary columns during ingestion with transformative spec transforms. Filtering and slimming data sources in ingest. By applying filters within transform spec filter and removing all unused columns in dimension spec dimensions, we keep our data sources lean and improve the possibility of higher rollup yield. There are a lot of things that I don't actually understand. For example, transform. I think this is specific process or phase in the process of query that's going to that Druid database will handle. Yeah, I need to keep looking at it. But well, I don't think it's that important to finish the article, so I'm going to skip it. I think the key takeaway is that they're minimizing data source that's going to be ingested into a Druid cluster for efficiency and optimally searching frequency if virtual ones. Well, this one it's kind of hard, right? Operate on physical columns. I don't know what physical columns and virtual columns. So I have no words on that. But this one, yeah, for example, use lookups rather than joins, which lookups operate on the memory and joins will actually go to the physical memory storage and refer to it. So, and also segmenting. So mainly keep the batches smaller and keep the data that's going to be taken in by the database smaller and use faster operations and stuff. That's what's actually saying it. And this one, broker to historical ratio, I don't know what the fuck it's saying. I think it's very in detail. I think it's I'm not really an expert of Druid, so I think it's very Druid specific thing that's going on right here on this one and basically everything, right? Use of multi-value dimensions. Exploiting the Druid multi-value dimension feature was key to overcoming the many-to-many combinational combinatorial. Is that a thing?
Combinatorial
quandary is like two. That's my impression. It's like two. No, what was it? What am I confusing with? I think it was something like quandic or something like that. Quandic is exactly the one that quandary. And also there's like university mathematics. It sounds like this quandary, which I cannot just remember right now. I don't know. Yeah, let's just forget about it. Quandary when integrating audience filtering and grouping functionality mentioned in the unevolving architecture section above. Together, these optimizations combined with previous ones have decreased our tail latency Druid by roughly 50%. That's cool. Validation and rolling out these changes to our metric system requires a thorough validation and release strategy. Our approach prioritizes both the data integrity and user trust, leveraging a blend of automation, targeted tooling, and incremental exposure to production traffic. At the core of our strategy was a parallel stack deployment. Both the legacy and new matrix stacks operated side by side within the Muse data microservices. This setup allows us to validate data quality, monitor real-world performance, and mitigate risk by enabling seamless fallback at any stage. Legacy new matrix stack. Muse data microservice parallel implementation to allow for control testing and rollout. We adopted two-pronged validation. Pronged. Automated offline validation. Using Jupyter Notebooks, we automated the sampling and comparison of key metrics across both the legacy and new stacks. Our sampling set included a representative mix, recently accessed titles, high-profile launches, and edge case titles with unique handling requirements. This allowed us to catch subtle discrepancies in metrics early in the process. Iterative testing on this set guided fixes, such as tuning the HL log K parameter and benchmarking end-to-end latency improvements. And also in-app data comparison tooling to facilitate rapid triage. We built a developer-facing comparison feature within our application that displays data from both the legacy and new matrix stacks side by side. The tool automatically highlights any significant differences, making it easy to quickly spot and investigate discrepancies identified during offline validation or reported by users. We implemented several release best practices to mitigate risks and maintain stability. Staggered implementation by application segment. Staggered. We developed and deployed the new metric stack in stages, focusing on specific application segments. This meant building our sorry. This meant building our support for asset types like artwork and video separately, and then further dividing by CEE phase, explore, exploit. By implementing changes segment by segment, we are able to isolate issues early, validate each piece independently, and reduce overall risk during the migration. Shadow testing, dark launch. Prior to exposing, what is that? Dark launch. Prior to exposing the new stack to end users, we mirrored production traffic asynchronously to the new implementation. We mirror production traffic asynchronously to new implementations. This allowed us to validate real-world latency and catch potential faults in a live environment without impacting the actual user experience. Okay. Okay. So what I understand here is that like when they execute some operations, what they will see is the legacy version, but at the same time they will expose that end users. We mirror production traffic. We mirror production traffic asynchronously to the new implementation. So what it does is to behind the scenes issue the traffic for the new implementation, meaning that they will run in the production environment, but that's not going to be displayed at the end users, right? That's why they call it dark launch or shadow testing, if I'm not mistaken. A granular feature flagging. We implemented fine grain. Hold on, let me. How do you say? Putting down the table because it's a levitating table. Levitating? That sounds super wrong. Let me search. Lifting. Okay, lifting table. Levitating sounded so wrong. Well, anyways, granular feature flagging. We implemented fine-grained feature flags to control exposure within each segment. This allowed us to target specific user groups or titles, instantly roll back or adjust the rollout scope if any issues were detected, ensuring rapid mitigation with minimum disruption. But what do you mean by segment in each software? Okay. Or segment as in targets, like user groups. So targets. Okay, right. So user groups or titles. Learnings and next steps. Our journey with Muse tested the limits of several parts of the stack. The ETL layer, the Druid layer, and the data serving layer, while some choices, like leveraging Netflix in-house hollow infrastructure, were influenced by available resources. Simple principles like offloading query volume, pre-filtering of rows and columns before Druid rollup, and optimizing search predicates, along with a bit of HLL magic, which I think it means row lookups. Went a long way in allowing us to support new capabilities while maintaining performance. Additionally, engineering best practices like producing side-by-side implementations and backward compatible changes enable us to roll out revisions steadily while maintaining rigorous validation standards. Looking ahead, we'll continue to build on this foundation by supporting a wider range of content types like live and games, incorporating synapses. I don't know what that is. Synopsis. Incorporating synopsis data, deepening our understanding of how assets work together to influence member choosing, and incorporating new metrics to distinguish between effective and authentic promotional assets and service in service of helping members find content that truly resonates with them. Okay, that was long. How long have I been? Okay, 1 hour. Okay. Yeah, this was interesting. A lot of things to learn. A lot of things that I didn't know. But what I found interesting is that, like, even though these tech stacks, which I didn't know, the basic principle to offload the transactions is kind of similar to like database optimizations, or well, back end or front end optimizations. Basically, keep the data small and keep the data and batches small, and use magic. Well, this was a very Druid specific thing, but sometimes there are similar things that magically libraries or software does its thing in a faster way for some reasons. For example, a bun, instead of using Vite or other ecosystems. Yeah. So yeah, I'll see you in the next article, which will be. Well, hold on. There, I opened a lot of things, so let me take a quick look at it. Okay, I read it, and I'm kind of interested in this. I will just wrap up after reading this. Software engineers often encounter problems which require dimension of all of small or moderately sized datasets which don't fit the label big data. To solve this problem, well, dissemination.
Dissemination.
Solve these problems, we often send data to RD relation database or new store query runtime, or serialized data is just a distributed cheap logical consumer. Yeah, scaling each of these solutions presents different challenges. Setting the data to an logical store or even memcache cluster may allow your data set to grow indefinitely large. But there are limitations on the latency and frequency with which you can interact with the dataset. Serializing and keeping a local copy can allow many orders of magnitudes lower latency and higher frequency access. But this approach has many scaling challenges. The dataset size is limited by available RAM. The dataset may need to be re-downloaded each time it's uploaded. Updating the dataset may require significant CPU resources or impact GC behavior. Netflix, serving many billions of personal requests each day, has a few cases for which the latency of a remote data source will be highly undesirable given the frequency with which those datasets are accessed. Netflix Holo is a Java library and a toolset for disseminating in-memory datasets
from a single producer to many consumers for high performance read-only access. Holo aggressively addresses the scaling challenges of in-memory datasets, and it's built with servers busily serving requests at or near maximum capacity in mind. Due to its performance characteristics, Holo shifts the scale in terms of appropriate dataset size for an in-memory solution. Datasets for which such elaboration may never previously have been considered can be the candidates for Holo. That was super hard English. Let me read it again. Datasets for which such elaboration may never previously have been considered can be candidate. Okay. So, okay, I understand. Small to medium dataset. Holo may be entirely appropriate for datasets which, if represented with JSON or XML, might require which might require in excess of 100 gigabytes. A good rule of thumb in 2017 kilobyte or megabyte, and often gigabyte, not terabyte or petabyte. In excess of 100 gigabyte. In excess. So it has to be like nearly over 100 gigabytes, not smaller. Okay, this is interesting. This was interesting. Let me sign in. I need to cut off the camera. Hold on. How can I cut off? Okay. Let me sign in. And I just want to bookmark it. How can I bookmark it? Here. Where does it go? System design? Yeah. It kind of relates to system design. Okay, there we go. We finished this article. I'm going to see you in the next recording. Bye bye. Ciao ciao.